Hello there and welcome to another video. In the last two videos I had a look at perspective, lenses and optics in general, and in this video I'm going to just look at one example. An example is of a lens focusing two parallel lines onto an image. So you can see in front of you a diagram representing a convex lens and a screen which we'll assume is at the focal length of the lens, which if you watched the other videos I made, you'll know that that means that the lens will focus points in the distance onto the screen. So let's zoom out and have a look at the parallel lines. So we've got two parallel lines and I've drawn a series of what are supposed to be coloured lights on them, and the lights go red, yellow, green, orange, purple, light blue, and then the same red, yellow, green, orange, purple, light blue. So there's 12 lights on each of the lines. So we want to know, where will the image of each light appear on the screen? Where will it be focused by the lens? Well, as we found out, all you have to do is draw a line from the light straight to the middle of the lens, go straight through, and where that line meets the screen, that'll tell you where that light will be focused. So let's put in some lines to find out where these lights will be focused. So 24 in all, and you can see I've color coded them so you can see the color of light coming from each of the lights. And you can see that I've got lines that all go right to the middle of the lens, pass straight through and then go onto the screen, so we can find out where the image of each light appears on the screen. Okay, so let's put them in. Again, there should be 24 of them. There we go, I think that's them all. Okay, so here are the images of each light as they appear on the screen. So if this was someone's retina, or they were focusing on a photograph or whatever, the image would show the two lines looking like they're getting closer to each other in the distance, just like we know they do. If you look at two parallel lines, they seem to get closer to each other in the distance. Now, obviously, in reality, in space, they don't get closer to each other. It's only the image of each light that get closer and closer to a point on the actual image. So these lights here, the image of each light is moving closer and closer to this point here. Now, we call this point the vanishing point for those two parallel lines. Now notice also that the lights on the image are getting closer and closer together as well. And that's what we see when we look at things in the distance. Although they're evenly spaced out, they seem to get closer and closer together. Now there's a few things I want to make clear about this. The vanishing point is here. It's on the image. That's where the vanishing point is. The vanishing point is not out here in space. It's not some finite distance away from the observer. Okay? The vanishing point is in the image. It's not out here. Some people think of the vanishing point as being at infinity. I don't think that's a very good way of thinking about it, but some people do, because the lights that are an infinite distance away on those two lines would both be focused at that point there. But that's a kind of an abstract idea, because you couldn't have two infinite lines like that. I think it's better just to think of it as a point in the image, because that's what it is. That's what it actually is. It's a point in the image. If these two lines were at a different angle but were still parallel, then they would have a different vanishing point. So if they were at an angle to the plane that the lens is in, or at an angle to a different angle to the screen, so those two lines are at right angles to the screen and the plane that the lens is in. If they were to say at a different angle, then their vanishing point would be a different point on the screen, a different point on the image. However, if I put more parallel lines in that were parallel to these two, then they would all have the same vanishing point. Okay? Every set of parallel lines has its own vanishing point in the image. The reason that we think the vanishing point is on the horizon, or we associate it with the horizon, is because most of the lines that we see are either horizontal or vertical. Now, most vertical lines that we see are too short to notice perspective, and horizontal lines will all have their vanishing point on the horizon. But there's nothing special about the horizon. It just so happens we live on a large surface, and that we tend to make lines either vertical or horizontal to that surface. But if you have a set of parallel lines at an angle, say beams of rays of light coming down from the sun, then their vanishing point will be somewhere in the sky, which is what you get with crepuscular rays. Now, something I've really got to make absolutely clear about, okay, is these lines aren't getting closer together in reality in space. It's only the images of the lines that look like they get closer together on the image. You can't then project a perspective image back out into space and have a look at it as if you can look at someone's perception of a perspective situation from the side. That is completely meaningless. As if you can go, well, it looks like those two lines are getting closer together, so we'll kind of think about what would it look like if we looked at this person's perception of the perspective situation from the side. Well, the two lines would be doing this, and the bottom one would be ramping up, and the top one would be angling down, and they'd meet at this point here, and this is the vanishing point. Okay, not to put too fine a point on it, that is total bollocks. It's meaningless. Okay? You cannot look at someone's perception of perspective from the side. The perspective is in the image. It's not in space, and you can't project it back out into space. And so many flat earth arguments are based on this ridiculous idea, and all arguments based on that idea are completely wrong. And they've been making this same bad argument for a very long time. You can find this on the Flat Earth Society website. Now, I think these arguments go way back to the first modern flat earther, I think, Rowbotham, who made these silly diagrams like this, where it's based on this idea that you can look at someone's perception of perspective from the side. It doesn't mean anything, so these arguments don't mean anything, because the vanishing point is not a finite point away. Now, there is such a thing as a visual limit, but that depends on how big the thing is you're looking at. If something's really big, you can keep seeing it for when it's really far away. If something's small, then it will become too small to be seen when it's not that far away from you. That's not the vanishing point either. That's just a visual limit. Now, this bad argument about the idea you can look at perspective from the side has been recycled again on YouTube by, like I looked in the last two videos, Brian Mullen, P. Brain, other people have done it. It's just nonsense. Okay, it's nonsense. It doesn't mean a thing. Now let's just quickly have a look at a perspective drawing, the actual image. Okay. Now here you've got a drawing with two vanishing points for two different sets of parallel lines for these cubes here. So this vanishing point on the left is where all these lines here look like they meet in the image of the observer. And this vanishing point on the right is where these parallel lines look like they meet in the image of the observer, or in the perception of the observer. Now it just so happens that the vanishing points here have been drawn on the horizon. They don't have to be on the horizon. It's just because these lines are all horizontal. Here you've got a 3-point perspective drawing. You've got two vanishing points on the horizon, so these lines are horizontal, but you've also got one that's, well, it's off the image, but these three lines here are going to meet at a point up here. So the vanishing point can be anywhere at all. You can any point in your visual field can be a vanishing point, and every set of parallel lines has its own unique vanishing point in your visual field. Okay? Right. Hopefully that's cleared that up. This absolutely ridiculous argument